All right, let's dive in. Data structures and algorithms.
Yeah.
Um, sounds kind of complex, right? But it's really all about how computers, well, how they organize and process info.
Hmm.
You've sent us like a ton of stuff, a whole YouTube course and code snippets and even like visuals. So let's jump in and see what we can find.
It's really interesting. It's like, this is core computer science, but it's actually like, it's everywhere. You probably don't even realize it. Like every app, every website you use, data structures and algorithms are like working behind the scenes.
Yeah, it's true. It's like the secret sauce,
Yeah.
like what makes technology actually like tick. One of the YouTube videos had this analogy, right? It said, imagine you're like organizing a bookshelf, and how you arrange the books, like by genre or by author, or I don't know, even by color, right? That's essentially like a data structure.
Yeah.
It's all about making that information easy to find.
That's such a good way to put it. And just like there are like tons of ways to organize a bookshelf, there are all these different types of data structures, and each one has its own like pluses and minuses. Just depends on what you're trying to do.
So there's no like one size fits all. Like there's a whole like toolbox of data structures to choose from.
Exactly.
The YouTube course, it broke them down into two main categories, right? Like linear and non-linear. Can you walk us through those a bit?
Sure. So linear data structures, they're basically the information is laid out like sequentially. Like imagine a line, think of like a numbered list. They're basically an array where each item has like a specific spot, or think of a chain where each link connects to the next one. That's a linked list.
Okay.
And some of those code examples you sent actually use arrays, like things like reversing the order of items or removing specific entries, stuff like that.
Oh, yeah. I see those now.
Yeah.
And those operations like reversing or removing, like are those considered algorithms? It seems like we're already kind of getting into algorithm territory here.
You got it. Each of those like code snippets, it's an algorithm basically in action, like a set of steps that the computer follows to mess with the data in a certain way. Now with nonlinear data structures, things get a little more complex. Instead of a simple line,
Yeah.
The data is organized in a more like interconnected way, like a tree, with branches or a network of nodes.
Okay, so I'm picturing like a family tree.
Right.
It branches out in all these directions,
Yes.
connecting like people across generations.
Yeah.
That's a good visual, right?
Yeah.
For a nonlinear structure.
Exactly. And the YouTube video talked about trees and graphs as like key examples of these nonlinear data structures. And graphs are especially interesting because they can like represent relationships between different pieces of data. Like think about your social media feed, right? Like Facebook or Instagram, whatever. It uses a graph structure to show you posts from your friends and like your friends' friends. It, links you all together.
Whoa, that makes a lot of sense. So data structures are like the foundation, It's how we organize information. But where do algorithms like come in? What's their role in all this?
Remember that bookshelf analogy we were talking about? An algorithm is like the set of instructions that you'd use to find a specific book, like on that shelf. So in the computer world, algorithms are the step-by-step guides that tell the computer how to solve a problem or, complete a task.
And you mentioned before that even those simple operations like reversing an array, that's actually an algorithm.
Yeah.
So it seems like algorithms are like everywhere in programming.
Totally. And just like there are different ways to find a book, right? You could browse by the author or the title or just, I don't know, wander around until you stumble upon it, right? There are often like many different algorithms that can solve the same problem. The real trick is figuring out which algorithm is like the most efficient. And that kind of brings us to the whole concept of algorithm efficiency, right?
And I'm guessing this is where things get maybe a little more technical. The YouTube course mentioned time and space complexity. Are those like the key factors, when we're talking about efficiency?
Absolutely. So time complexity, it's all about like how long it takes for an algorithm to run, like how many steps it needs to, to actually complete the task. And then space complexity focuses on how much memory the algorithm uses while it's doing its thing. Ideally, we want algorithms that are like super fast and use the least amount of memory possible.
Yeah, that makes sense. We want our computer to be like snacky, and not like hogging all the resources. One of the code examples that you sent, it actually shows two different algorithms for finding the sum of like natural numbers. And one uses a loop and the other one uses a math formula. And the formula is way faster. So this goes to show like why it's so important to understand, that time complexity.
Exactly. And to like describe this efficiency in a standardized way,
Right.
computer scientists use something called big O notation. And it's kind of like a shorthand for comparing how different algorithms, scale as the amount of data grows.
So big O notation, it's like a decoder ring for algorithm efficiency, right?
Yeah.
Helps us like see which ones are fast and which ones are maybe a bit slower. But before we like get too deep into that, some of those code examples you sent were really cool. Like that one for reversing a singly linked list, that was like, I don't know, it seemed like magic.
Yeah, it's a pretty neat solution, and it really shows you how like understanding how the data is structured, can lead to some pretty efficient algorithms. In that case, the algorithm uses these two pointers, right? It's like imagine two fingers running along the linked list, and they're like swapping the data at each spot until they meet in the middle, and that effectively, reverses the whole list.
It's amazing what you can do with like just a few lines of code when it's well written. I'm starting to see why people like get so excited about this stuff.
Oh yeah, definitely. And these code examples really highlight how algorithms are used, in real world situations. Like sorting algorithms, for example, those are like essential. They arrange data in a specific order and you see them everywhere, like presenting search results online or like managing those huge databases behind the scenes.
Speaking of real world applications, one of the examples was about finding a missing number in a sequence. It was kind of like a logic puzzle.
Yeah, exactly. And that's what makes algorithms so like engaging. Is like they're these elegant solutions to these like logical problems, and you can apply them in all sorts of different situations.
Okay, so I'm feeling like a little more confident about this whole data structure and algorithm thing. But big O notation, I gotta admit, it still seems a bit mysterious. Can you help me out with that a bit?
Sure. Think of it this way. Imagine you're comparing different cars. Okay, some cars might be really fast, but they use a ton of gas. Others might be more fuel efficient, but they're not as speedy. Big O notation helps us compare the fuel efficiency of different algorithms. It tells us how the algorithm's performance changes as, the amount of data gets bigger and bigger.
Okay, that car analogy, that helps a lot. So is it always better to have an algorithm with a lower big O notation, like one that's more, fuel efficient?
Well, it depends on the situation. Sometimes an algorithm that's like slightly less efficient might be like easier to understand or implement. It's kind of like choosing between a compact car for driving around the city versus a big truck for like heavy stuff. You got to choose the right tool for the job. You know what I mean?
So there's always a trade-off. Just like in real life,
Yeah.
You got to weigh the pros and cons to find the best solution for what you're trying to do.
Exactly. And that's what makes this whole field so interesting. It's not just about memorizing like formulas or code. It's about understanding the core ideas and then using them in creative ways to solve, real problems.
This is so cool. But I'm also like curious about how these basic concepts, apply to things like web development. Is there like a connection there?
Oh, absolutely. Data structures and algorithms, they're like the backbone of a lot of web technologies. Like, think about searching for information online. Search engines use these really sophisticated algorithms to, like, index and retrieve web pages that are relevant to, to what you searched for.
Yeah.
Or online shopping, right? Algorithms are behind those recommendation systems, the ones that suggest products based on your browsing history, stuff like that.
Wow. I never really thought about how much of my like online experience is shaped by these behind the scenes algorithms.
Yeah, it's pretty amazing how widespread they are. And as web technologies keep developing, understanding data structures and algorithms is going to become even more important for both developers and users.
Well, after this deep dive, I'm definitely feeling like more prepared to navigate the digital world. We've covered so much already.
Yeah.
From like basic data structures like arrays and linked lists to those like more complex ideas like big O notation and even how these concepts are used in things like web development.
And we've just, scratched the surface. There's a whole universe of algorithms and data structures out there, each with its own like corpus and uses. The more we explore, the more we discover how these concepts really underpin so much of our, technological world.
We've talked a lot about those linear data structures, especially arrays, and touched on nonlinear ones like trees and graphs. But there's one more type that the YouTube course mentioned, stacks and queues. They sound like data structures, but they also have a kind of like everyday feel to them. What's the deal with those?
They do sound familiar, right? It's because like how they work kind of mirrors those real world scenarios. Think about a stack of plates, you know? You can only add or remove plates from the top. That's the whole idea behind a stack data structure. Last in, first out, or LIFO for short. Queues, on the other hand, they work on a first in, first out, or FIFO principle. Like, think of a line at the grocery store. The first person in line gets checked out first.
So stacks are like a pile of plates and queues are like a line at the checkout.
Got it.
But how are they actually used, in programming?
Stacks are, they're super useful for managing function calls in a program. When a function calls another function, the computer needs to keep track of, where to return to once that called function is finished. And a stack is like perfect for this because the last function called is the first one to return.
So it's like a trail of breadcrumbs, right?
Yeah.
Helps the program retrace its steps.
Exactly. And queues are often used in situations where tasks need to be processed in a specific order. Like imagine a printer queue, where lots of users are sending documents to be printed. The queue makes sure that those documents are printed in the order that they were received.
Okay, those examples make it like way clearer how stacks and queues work in practice. And it seems like there's a data structure for almost every scenario you can imagine. We've covered linear structures like those arrays and linked lists, the nonlinear structures like trees and graphs, and now these like specialized structures like stacks and queues. It's like a whole data structure zoo out there.
It really is. And the cool thing is the zoo is like always growing as we run into new challenges and, come up with new algorithms to solve them. It's a really dynamic field with tons of exciting possibilities.
One of the code examples we haven't really talked much about yet is resizing an array. Why would you even need to do that?
That's a great question. It really highlights like a key limitation of arrays, their fixed size, When you create an array, you got to say how many elements it can hold. But what if you need to add more elements than the array can handle? That's where resizing comes in.
It's like, you realize your bookshelf's full and you got to get a bigger one so you can fit all your new books.
Yeah, exactly. And just like with bookshelves, resizing an array, it's like it can be a bit of a pain for the computer. It has to create this whole new, bigger array and then carefully copy all the stuff from the old one over and then update any references to that array. It's there are definitely times when other data structures like linked lists, they offer more flexibility because they can grow or shrink, dynamically.
Yeah.
But arrays have their advantages, especially when you need to access certain elements quickly.
It's that, that classic trade-off, right? Efficiency versus flexibility. Got to pick the right tool for the job. And sometimes that means, weighing those two things against each other.
For sure. And that's what makes this whole area so interesting. It's not just about memorizing a bunch of formulas or, code.
Yeah.
It's about understanding the ideas behind it all and then, using them creatively to solve problems, real world problems.
Speaking of creative problem solving, there was that code example about moving all the zeros in an array to the end. It sounds simple, but the solution was surprisingly clever.
It is. That one really shows how powerful it can be to use multiple pointers to, manipulate data efficiently. So in this case, the algorithm uses 2 pointers, one to go through the array and the other one to keep track of where the next non-zero element should go. It's kind of like having this helper that neatly rearranges everything as you go.
We've covered so much. Linear structures like those arrays and linked lists, nonlinear structures like trees and graphs, and even like those specialized structures like stacks and queues. It's really amazing to see all the different ways there are to organize and process information.
And what's even more exciting is that this whole field is always changing. As we face new challenges and create new technologies, we're going to need even more, innovative data structures and algorithms to make all that stuff work.
This deep dive has really opened my eyes to the world of data structures and algorithms. It's like I have this new perspective on how technology works, and I'm already starting to see these concepts everywhere I look.
That's the great thing about understanding these, basic concepts. It gives you this new way of seeing the world, of understanding the building blocks of the technology that's, all around us.
So we've covered a lot today. From those basic data structures to the importance of algorithm efficiency and even how these concepts are used in things like web development. I feel like I've got a good grasp on this, fascinating subject now.
And remember, this is just the start. There's a whole world of algorithms and data structures out there just waiting to be explored. The more you learn, the more you'll appreciate the cleverness and the elegance that goes into, making technology work so smoothly.
Well, that's a wrap for our deep dive into data structures and algorithms. We hope you enjoyed this exploration and learned some cool stuff along the way. If you have any questions or want to dive even deeper into this, please reach out. We're always happy to keep learning